going to take a look at the binomial distribution, one of the most important topics that we're going to study this year, and something that is virtually guaranteed to show up on the AP test at least a few times. So the first thing to know about the binomial distribution is that it is a discrete probability distribution, and there's really four main conditions that need to be met for something to be considered binomial. So I like to think of this in terms of the binomial checklist. So if you remember the acronym BINS, that can help you remember the conditions that need to be met for a distribution to be binomial. The first one is B for binary, which means that there are only two outcomes. Typically we refer to them as success and fail. I for independent, meaning that each trial is independent from every other trial. N for N is constant, meaning that there is a defined number of trials, which we use the letter N to represent. And S for same probability, meaning that the probability of success, referred to as P, is the same for each trial. If a distribution meets these conditions, we can call it binomial, and we use the notation really similar to what we did for the normal distribution. This time we use a capital B, and in parentheses the two parameters N, P, N for the number of trials, and P for the probability of success. So let's take a look at an example then. So let's imagine that you're going to be taking a quiz. It has 5 questions on it, multiple choice, with 5 choices, A through E. We're going to assume that each question has only one right answer and that there's no pattern or anything to where these correct answers are. And let's say that you have no idea what's going on, so you're just going to completely guess every single time. Well, does this fit the binomial checklist? Well, let's go through and check each one off. B, binary. Are there only 2 outcomes? Yeah, you're either correct or you're incorrect. I, independent. Can we assume that each question is independent from the next? I think that's safe to assume. N is constant, so there needs to be a set number of trials. Well, there are 5 questions, and the same probability of success, and since there are each 5 choices, you have a 1 in 5 chance of guessing the correct answer in every one. So this satisfies all the 4 conditions for the binomial checklist. So we have a random variable here, x, standing for the number of correct answers. And this is going to be a binomial distribution where n is 5 and the probability of success is 1/5 or 0.2. So we have a binomial distribution with n is 5 and p is 0.2. Since this is a discrete random variable, we can express this in a table. And what are all the possibilities for x? Well, we could have x is 0, you don't get any right, 1, 2, 3, 4, or 5. So the next thing I want to think about is how do we calculate what these probabilities are? So the first thing to think about, what's the probability that x is equal to 0, that you don't get any right? Well, knowing that these are independent, that would mean that you got every single question wrong, and because they're independent, we can multiply those probabilities together. So the first question is 0.8 to get that wrong, 0.8 to get that wrong. Do that for 5 questions, basically you have 0.8 raised to the 5th. And that would be the probability that you got all of them wrong. And that has a probability of approximately 0.328. So the probability of x being 0 is 0.328. Now the next one, this is where it starts getting a little more complicated. Let's take a look at the probability that x is equal to 1. That is the probability that you get 1 question correct. Well, it might be intuitive to kind of think about this in terms of, well, that means that I would get a question right, so 0.2, and then I would have to get 4 questions wrong, so 0.8 raised to the 4th. So that's 1 question right and 4 questions wrong. And that would be a probability of 0.0819. But let's think about this one a little bit deeper. This statement right here would be kind of saying that we're getting the first question right and then the last 4 questions wrong. But that's not the only case that we could have. Think about this in terms of each of these questions. We could get the first one right, and then the last 4 wrong. But that's not the only way to get one right. We could get the first one wrong, the second one right, and then the last 3 wrong. Or we could get the first 2 wrong, get the third one right, or maybe we get the fourth one right. Or maybe we get the 5th one right. So if we only look at this in terms of 0.2 times 0.8 to the 4th, that is only looking at getting the first one wrong, or I'm sorry, the first one right and the last 4 wrong. But there's how many ways to get one right? Well, there are 5 ways to do that. So really what we need to do is take this 0.2 times 0.8 to the 5th, or to the 4th, and multiply it by 5, since there are 5 ways to do that. So the probability is actually that times 5. So it's important with the binomial distribution to consider all of the ways to get that specific number of successes. Alright, now what if we take a look at the probability that x is equal to 2? Well, let's think about how many ways could we get exactly 2 questions right. We could get the first 2. We could get the first one and the third one. Get the first one and the 4th one. The first one and the 5th one. Or we could get the first one wrong, get the next 2. Get the first one wrong and get the 4th one right. So what are all these different combinations we have of getting these questions? So we get the first 2 wrong, then the next 2. So that should do it for all of the different combinations of getting these questions right. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. So there are 10 ways to get 2 questions correct in this case. So what we need to do for the probability that x is equal to 2 is we'll take 10, because there's 10 ways to get them right, times 0.2 squared, since we got 2 questions right, times 0.8 to the 3rd, since we got 3 questions wrong. And this is how a binomial probability gets calculated in general. This probability would be 0.2048. So there's really 3 parts of the binomial probability. And we're going to generalize this and kind of go through it, instead of counting out and listing out all the ways, we're going to find a faster, more efficient way to get this value here. So there's really 3 parts of this calculation going on, and that's what we're going to generalize pretty soon in a formula. We have this first number here, that is how many ways could you see a certain number of successes. Then we took the probability of success raised to how many successes we had, times the probability of failure raised to how many failures we had. And in general, this is the form that we're going to see for the binomial probability formula. So before we get to that formula, we need to take a look at something that you might have seen in class before. It's the idea of n choose k. N choose k is the number of combinations to get a certain number of successes out of a certain number of tries. For the binomial formula, what we're going to be looking at is the probability that we have k successes, where k is just some number from 0 through n. That would equal the probability that we see that many successes is n choose k, how many ways to have that many successes, times p raised to the, times p raised to the number of successes, which is k, and times 1 minus p, the probability of failure, to the number of failures that we have. Well, if we had started with n trials and k of them were successes, well then n minus k would all have to be failures. So this right here is the binomial probability formula. the probability of seeing exactly k successes is equal to n choose k times p to k successes times 1 minus p to n minus k failures. It's kind of a complicated formula, but it's almost best to reason through it. I think it makes more sense if you think about what the formula means rather than necessarily having to use that, memorize it letter by letter, and plug things in. Now, I should mention this is one of the formulas that's given to you on the AP formula sheet. And let's go ahead and fill in the rest of these. So the probability then that we have x is equal to 3 successes, is out of 5 trials, seeing 3 successes, so 5 choose 3, times 0.2 raised to the third, times 0.8 raised to the 2, because there were 3 successes, so the other 2 had to be failures. Is 0.0512. Let's do this one more time for the probability that x is equal to 4. So that is going to equal 5 choose 4 times 0.2 raised to the fourth, since there's 4 successes, times 0.8 raised to the first power, since there's 1 failure. And that is a probability of 0.0064. And then finally, we'll take a look at one last one, the probability that x is equal to 5, that you get all 5 right. So that is 5 choose 5, which is really just 1. There's only one way to get them all right. Times 0.2 raised to the fifth, times 0.8 raised to the 0, because we didn't get anything wrong. And that probability is 0.00032. Now that we have this kind of broken down in a table, we can answer some questions about probability. So for example, what is the probability that you get at least 3 questions right, greater than or equal to 3? That would be passing. That would be a 60%. It would be a D, but it would be technically passing. So what's the probability that we see exactly 3 or more? Well, knowing what these are, we could have 3 correct, which is 0.0512, plus getting 4 right, 0.0069, plus getting 5 right, 0.00032. So the probability that you pass guessing on every question is 0.0613. So not very likely that you would pass just by guessing.